Welcome everyone to today's Keeping Current seminar. And we've got what I expect will be very interesting talks by, in this case, both students. And let me introduce Nelson Penn, who will tell us something about the game of Nim, which I remember seeing years and years ago and deciding that I couldn't figure out a good strategy, so I never played it. So Nelson will tell us why I never figured out a good strategy, maybe. Take it away, Nelson.
Sure. Just making sure. Can you all hear me okay?
Yes.
Okay, great.
And you should be able to share your screen as well.
Right. So I'll just share my desktop. Okay. So here we go. So I'm going to talk about the game of Nim and many variants thereof. So first of all, I'm going to talk about the original game of Nim. And this game is pretty straightforward. There's a few stacks of sticks or rocks or chips, whatever you like to call them. I usually call them chips rather than sticks, so that way typos aren't so dangerous. But it's a two-player game, and it's played by alternating. Each player will choose a stack and take a certain number of sticks or chips out of it. And so the game ends when one player takes the last chip and wins. So I prepared a quick example so that you all can play it against a very good AI named Jeff, which just so happens to be my cat's name, but that's irrelevant. So anyone who likes to participate, please throw out moves you'd like to make and see if you can beat Jeff.
Let me take two chips out of the first pile, the 3 pile.
All right. So then in response to that, Jeff takes 1 from the first stack. Leaves you with 0 on the first, 5 on the second, and 4 on the third.
Someone else?
I would take 4 from the next pile.
4 from the middle pile?
Yeah.
So in response to that, he takes 3 from the second stack, or from the last stack, and you're left with 0, 1, 1.
I think I'm used to the variant where the last person to take a chip loses.
Yeah, there's that variant too, but I generally use take the last chip because the winning strategy is all the same except for the last move. So anyone care to make the last move?
I knocked my king over.
Make a losing move.
Right.
So take 1 from the second stack.
So in which case he would win. So that's the game of Nim, and I'll let you have a rematch later if there's time, once I've ruined the game properly for you all. So let's get back to the theory behind it. So Nim is one of a larger class of games called Impartial Games. Now, Impartial Games have a couple shared properties. One is that they're completely deterministic, no randomness, and so you can expand the entire game tree if need be. The second is that the difference between players is only who goes first. It's not the moves available to a player don't depend on the player, only the game state. And then the third requirement is that these games cannot be infinite. So you can't make a move where you do nothing. So some examples of impartial games are Nim, which I just showed you, and Sprouts, which is another mathematical game that includes connecting lines, and a lot of other games you've probably never heard of. Impartial games are slightly less popular, maybe because they're simpler, but also they have interesting mathematical properties. So some games that aren't examples are chess, Go, shogi, dots and boxes. Most of the games you might play are poker as well, because it has randomness. And the ones I've listed here are not impartial because they're two different sides of the board. So players will have different sets of moves. White has one set of moves, black has the other. So then I will introduce the Sprague-Grundy function. Now, this is where I start to slowly ruin these games for you. So the Sprague-Grundy function is a way of providing a value to a state in an impartial game. So it depends on this definition of the minimum exclusion, which the minimum exclusion of a set is just the smallest non-negative integer that's not contained in it. So the Sprague-Grundy value of a position is simply the minimum exclusion of the Sprague-Grundy values of each state reachable from that position. And so a quick example, if you can move to states with values 0, 2, and 3, then the Sprague-Grundy value of the current state will be 1, because 1 is the first integer not included in this set. Now, a Sprague-Grundy value of 0 is very special. It's what I will call a zero position for obvious reasons later, but it means if a position is a zero position, the player who just played would win, and the player next to play would lose, assuming they're both playing the optimal strategy. So assuming everybody plays perfectly, the winner is known beforehand. So there's several variants on Nim. Well, very, very many variants on Nim. One is Fibonacci Nim, where you play on a single stack. The first player obviously can't take everything, but after that, if a player takes some number of chips, the next player can take up to 2 times that, but no more. And then circular Nim is a different variant where it has n stacks, and you can choose from k adjacent stacks. So this over here is circular Nim on 12 vertices, where you can pick from 3 adjacent vertices. So you could say pick these 3 adjacent vertices and take any number from them, as long as you don't pick 0 from everything. So the question is, well, if we can use the Sprague-Grundy function to get the winning strategy every time, why do we study these? But the reason is, oftentimes, we can represent the Sprague-Grundy function with something similar, or use a simple function to determine whether a position is winning or not. So in the case of Fibonacci Nim, the winning positions are Fibonacci numbers, hence the name. So if a position has 8 chips, if the game has 8 chips, it's a 0 position, meaning you want to always end your turn on a Fibonacci number. And for circular Nim, there are these simple relationships found for certain cases, not in general for a general n and k yet. So those are some examples on the slide of some certain positions that have simpler ways to find the winning positions. So now it's time to ruin regular Nim for you. So base Nim, you can find the Sprague-Grundy function exactly with the exclusive OR of all of the stacks. So in the game we just played, the stack values were 3, 5, and 2. So you apply binary exclusive OR to these values to receive the Sprague-Grundy value. So that gives you a way to win every time, as long as you start on a non-zero position. Just end your turn where the exclusive OR of all of the stacks is 0. So now let's mention a little bit about why Sprague-Grundy function is well defined. And this is because of the restrictions of impartial games. In fact, it only applies to impartial games. One of the reasons is the game cannot be infinite. Because if you have a state that you can make a move to itself, then it would be the Sprague-Grundy value would be the minimum exclusion of the Sprague-Grundy value, which would mean that it's undefined. So that's why the game can't be infinite. And then also the game has to be deterministic, because since the Sprague-Grundy function is recursively defined, you have to be able to expand the entire game tree. Now, I'm going to address the elephant in the room. I haven't mentioned anything about this yet, and I know it's a burning question on everyone's minds. And that is, where are the graphs? Because we're already to slide 9, and no graphs have shown up. I need to introduce them. So what if we play Nim on a graph? Or better, a simplicial complex. So a simplicial complex is a superset of vertex edge graphs. And in addition to it having vertices and faces and edges, it can also have faces of more than 2 vertices. So one extra requirement on that is that if you have a face of the complex, every subset thereof must also be a face. So a quick example of a simplicial complex, we can define a simplicial complex that represents a cube. So the faces of this would include, 1, every vertex. Sorry, I accidentally drew a line there somehow. And again. Well, every vertex, every edge, and then every face of the cube. So we would have to include this square as a face. But in addition to this, because every subset has to be a face, we also need to include some maybe less intuitive faces, which are these faces of 3 vertices on the cube. So we would have to include every group like this. Now, how do we play Nim on this? Well, the answer is we put stacks of chips at each vertex. And then you pick a face, and you can remove a certain number of chips from every vertex of the face. So now I'll move on to my work, which focuses mainly on this special variant of Nim called Simplicial Nim. So I've written my code base entirely in Rust, which I highly suggest if you haven't tried it out. It's a great way to write very foolproof programs, or at least very fool-resistant programs. It kind of forces you or encourages you to handle every case, which is very nice for this. But anyway, the main function, the core part of my work is computing the Sprague-Grundy function and computing it fast. Now, this isn't anything new theoretically, but it's used in all other parts of my project, and it's something I needed it to be efficient and reliable. So I implemented this recursive definition, but I also added several speedups due to known results about certain patterns in positions, when we can stop early, and stuff like that. And I've also added some maybe more mundane optimizations to it, such as reducing copying as much as possible, memorization, and removing symmetries as a pre-processing step. So this is used in the other extensions of my work, and one of those is the function suggester. So when I am analyzing these games, what I end up with is the Sprague-Grundy function for tons of positions on the game. And I thought it would be helpful. Well, it's kind of hard to see these patterns on a first glance, because what I want to do is find a proof that I can prove a class of 0 positions for a game where they're unknown. So I wanted to bring in some computational power to help me. So what I did was I came up with this way of, well, if I want it to be a relationship with elementary operations, then why don't I have the program try to find elementary relationships between the stack values that tells me whether a position is winning or losing. And so I made this mini assembly language that, and then performs searches on programs to give me a program that does just that. It'll take in a position on the game, and it'll return a 0 if it's a 0 position and 1 otherwise. And the idea is I'll look at the result of this. If it finds a program, it's most likely going to be correct, but it's not for sure. So I follow this up with manual verification and a proof. So this is the assembly language that I created. It's got all the operations needed for elementary functions of the stack values. And of course, because it needs to be able to access the stack values, there's another operation for loading the number of chips in stack X, per se. So I'll give you a quick example of how it works. Well, so this is, oh, crap. I didn't mean to go forward that much. This is the path 3 complex. So it's a simplicial complex, which just so happens to be a normal vertex edge graph. And it's a simple case that I use to demonstrate a lot of the functionality of what I've written. So the first step for using the function suggester is I generate the Sprague-Grundy function for a lot of positions. So I generate the Sprague-Grundy function for all positions A, B, C, where A, B, and C are some values between 0 and 8, which results in 512 positions. I mean, of course, this isn't infinite positions, which is why I can't say that the program is correct from the start, but it's most likely going to be correct, and I will verify that later. So then these are passed to the function suggester. So the function suggester does a search on those mini assembly programs and finds one that does what I want. It classifies all the winning and losing positions. And so the output of this for the path 3 is this program, which is actually a bit more clever than the program that I would write for this topic. And it uses right shifting off the right side to reduce the number of operations, which, I mean, makes sense because I search on length of program first. So this tells me, this little program tells me, load the right stack value, load the left stack value, do Boolean equality, which pops those off the stack, and just like a normal assembly language, then put the middle stack value, right shift it, and Boolean not. And the specifics don't really matter that much, but I'll show you. I can look at the output of this. It gives me a program that successfully classifies the subset of positions that I explored, and then it leads to intuition and a manual proof. So I'll show you the proof. So this is saying all the winning positions are where the middle value is 0 and the outside values are equal. And so this is proof's pretty straightforward. So here is the first case. If the middle value is 0, then it's regular Nim on 2 vertices. And so we know the Sprague-Grundy function of regular Nim is just the exclusive OR of the stack values. So this is going to be a winning position if and only if these 2 stack values are equivalent. And so, well, what about the other case? The other case is when the middle vertex is not 0. But we can easily see if the middle vertex is not 0, we can move to a 0 position. Oh, man. We can move to a 0 position as we had before. And because of the definition of Sprague-Grundy function, if you can move to a 0 position, this position is not. So that confirms the intuition. If the middle vertex is not empty, it's not a 0 position. So that means for this path 3 complex, it's a zero position if and only if the middle vertex is 0 and the outer vertices are equivalent, which, great. I use the function suggester to help me, and then that leads to intuition. Well, what about a larger example? So this is the projective plane complex. I mean, it's not really a projective plane, but it has its nickname because in this picture, the outer vertices are equivalent. So these two vertices are the same, these two vertices are the same, and so on. There's wraparound. And the reason why this graph is so interesting is because there's some well-studied vertex-induced subgraphs that cannot occur in this. So it's likely I'd be able to find something new. However, the set of zero positions for this are very complex, and I've been able to group some simple cases, but a lot of them defy patterns. And my function suggester hasn't found a program that successfully classifies them all magically either. So I'm of course still in the I'm still optimizing this, and hopefully I'll be able to get some better results with either this complex or maybe a medium one in the future. And I would be very happy to have even a simple proof of a previously unclassified case of like class of zero positions for a Nim game. And so one more extension to the project is symmetry removal. So there's thousands and thousands of zero positions that I come across on especially the projective plane complex. And it would be great to only see a subset of that, because when two zero positions are zero position for the same reason, I'd like them to look the same. But since there's 60 symmetries, there's that class of zero positions and lots of permutations thereof. So I can remove symmetries from the search phase, which I already do, but also it's helpful to remove symmetries for visual inspection as well. Now, there's lots of work done on removing symmetries in graphs. And it's a very well-studied problem, but that's not really what is necessary for my project. I don't need something super fast to remove these symmetries. However, I'm wondering if it does break patterns in the data. So something I've come across is when I remove symmetries, I'll have a random scattering of positions that are of the same class, but different permutations thereof. And I'm not going to go too in-depth into this for sake of time, because I'm sure my presentation slot is ending soon. But I've been looking into ways to have like a semantically aware symmetry removal, so that positions of the same class will look similar rather than having being a bunch of different permutations of that. And I've been looking into concepts from group theory and stuff like that for doing that. And I've made some progress, but I'm also not quite sure that the problem is well defined. And it's worth looking into though. And it would be very helpful for both the function suggester classifying the zero positions and me classifying the zero positions. So that is the end of the presentation. I was wondering if anybody has any questions. And also, if you want, you can rematch Jeff now that you know the how to beat him.
Well, first, if there are questions, I'd like to ask how you go about computing the SG values for the subset of all possibilities. Do you start with a win and then move backwards from that into positions that would have led to that win in order to figure out the SG value, or is there some other technique?
Well, yeah. So what I do right now is that. So I mean, I just use the recursive definition of the Sprague-Grundy value. So I start from the position I want to get the Sprague-Grundy value of, and then recursively compute for the states reachable from that. But I also have speedups, like I mentioned. Like, for example, if there's a circuit in the graph, I know that if the current position is like a number times the circuit, so like 1, 1, 1 along a circuit of the graph, I can say that it's a 0 position early. So I use the recursive definition of the Sprague-Grundy function directly, but I also have extra speedups that work in the case of Nim.
And you must use caching or memoization as you're doing that.
Right, yes. And I also use memorization. Whenever I calculate a Sprague-Grundy value, I put all symmetrical permutations of that position in the memory as well.
Right. Now back to that example where you had just 3 nodes connected by simple lines. There is a symmetry there. The outer nodes are symmetric with each other.
Yeah, yes, there is.
And do you take advantage of that then when you have the SG function for a particular setting, that you know that it's the same for the symmetric setting of that?
Yes. So it's a the symmetries is a pre-processing step for the actual calculation of the Sprague-Grundy function. So there's one symmetry other than the identity for this graph, which is 2, 1, 0, which means you can flip it sideways. If this is stack 0, 1, 2, then we can reverse them. And so whenever I calculate a Sprague-Grundy value, I insert that Sprague-Grundy value for this graph, and then also the flipped version in the memory. Does that make sense?
Yeah. And I had one other question. Early on, when you were defining the Sprague-Grundy function, it didn't look like 0 was even a valid value because it was the first non-negative.
Well, it is a valid value.
A non-negative, I see. It wasn't it wasn't non-0. It was, non-negative. So 0 is a valid value. Okay. A silly question. Sorry about that.
No, it's perfectly fine.
So if we have then a position which has a value 0, then let's look at that red definition. That means that 0 is the largest let's see, if there's a move from that position to somewhere else, it also has a 0. All right. And when there's no moves left, and that means someone has won.
Right.
Do you then define the Sprague-Grundy value of that position to be 0?
Yes, yes.
You have to have a base for the recursion.
Yeah, the base for the recursion is if there are no moves, it's a 0 position.
I see. Okay.
And
or anything which can lead to that when I move and then someone else moves, then if it would lead to that, then I also have won.
Right.
But that's if the other person did the very best possible. So it's a bit like a minimax.
Yeah, you have to end your turn on a 0 position every time to play optimally.
Right.
And in fact, in my implementation of Jeff, he is playing optimally. And so if he starts his turn on a 0 position, then he'll stall. Because if his turn starts on his 0 position, that means the only thing he can do is wait until the opponent messes up. So if his turn starts on his 0 position, he stalls. Otherwise, he moves to the lowest 0 position, the 0 position with least chips.
And he stalls by making a smallest possible move.
Right.
Taking one chip from somewhere. Yeah.
Yeah.
Got it. Yeah. Right. Other people have questions.
Yeah. I do have a quick question. Nelson, do I understand then that whenever you actually obtain a negative result, your function suggestor, well, maybe I will first ask this. You told me that for this complex, you generated 90-some million of positions, right?
It was like 16 million
Okay,
for
16 million, all right.
this
And-
complex.
Right, and then you are looking through essentially functions that you can define using your assembly language.
Right.
And at some point you say, okay, after searching through this particular search space of those functions, none of them classifies correctly winning positions.
Well, the search space of assembly programs right now is infinite, or at least
Yes,
finite, restrained by the computer's hardware.
Right. But at some point you could say, I have searched through all programs of length at most 5.
Right. So then that would rule out any program.
Correct, yes. So in
running.
fact, you are obtaining quite a number. So far, you have obtained quite a number of negative results. Namely, you can say that none of functions in the particular class can possibly work as a Sprague-Grundy function for this complex.
Right.
Okay, I just wanted to be clear. So in fact, even negative results do tell us something.
Right.
That you have already. Mm-hmm.
Good. Well, we're out of time. I'm sure that people will want to ask you questions in addition, but we'll have to take those offline. Thank you very much, Nelson. That was a fascinating talk.
No problem.